All right, hello everyone, welcome back. We are still in section 3.9. Let's do this example. Let's find the antiderivative of the cosine of x over sine squared of x dx. Okay, I don't directly have a rule for that. Okay. So I need to somehow rearrange this so that it fits the form of one of the rules that I know. So let's see, I could rewrite this possibly as the antiderivative of maybe cosine of x over one of those sine of x's times 1 over sine of x, because I have two sine of x's multiplied together in the denominator. And why does that help me? Because this is equal to cosine of x times the sine of x, which is the cotangent of x, times 1 over sine of x, which is the cosecant of x with respect to x. Now that one I have a rule for. I know that the antiderivative of cotangent times cosecant is equal to negative cosecant of x plus c, of course, because I'm taking the indefinite integral. All right. So that is one example of how we had to rearrange the function so that it fits the form of a rule that we have to apply rules of antidifferentiation. A word of caution here. I'm going to put this in bold. Do not do the following, because it will give you an incorrect answer. If you're given this function, cosine of x, sine squared of x, dx, you might be tempted to sort of distribute that integration symbol. You might be tempted to rewrite this as, say, integral of cosine of x dx over integral and then you might think, well, integral of cosine is sine, right? Sine of x, integral of sine is cosine, so integral of sine squared, well, maybe that's negative cosine squared of x plus c. But using trigonometry to rearrange this, to apply the rules that we have, gave us this function, negative cosecant of x. This function is not at all the same as this function. These are not the same. So perhaps that gives you a little hint that the antiderivative or integral of a quotient cannot be found by taking the quotient of the antiderivatives, just like with differentiation. Remember, we had certain rules that told us how to find the derivative of a quotient and the derivative of a product. Well, that same principle applies here in that I cannot distribute this this antiderivative over a quotient. So don't do that. It will lead you astray. All right. One more problem in that same vein of thought. If I want to find the antiderivative or indefinite integral of 36x to the 6th plus 16x to the 5th divided by x to the 4th dx. Okay? This is a rational function. It is a quotient of two polynomials. I do not have a quotient rule for antiderivatives, at least at this point. Turns out that there actually is not one, but we'll get to that later. So I have to rewrite this somehow. I can rewrite the integrand, this part here, as 36 x to the 6th over x to the 4th plus 16 x to the 5th over x to the 4th dx, which I can simplify. This is equal to the antiderivative of 36x to the 6th over x to the 4th is 36x squared plus 16x to the 5th over x to the 4th is 16x. And I'm taking the antiderivative of that with respect to x. And these two, I have rules for taking the antiderivative. All right. And also, just similar to what we did in differentiation, you will probably get to the point where you don't rewrite these as two separate integrals. You just kind of do that part in your head and go ahead and apply the rules of antidifferentiation to both parts. So let's do that here. This is equal to that constant 36 times the antiderivative of x cubed, which is equal to x to the increased power of 3 times 1 over that increased power of 3 plus that constant of 16 times x to the, I'm increasing the power by 1, 1 plus 1 is 2, times 1 over that increased power of 2, and this whole thing I add c to, which I can simplify, and I get 12x cubed plus 8x squared plus c. And I could check that if I wanted to. If I found the derivative of this expression and I tried to add the two terms by rewriting them with a denominator of 4, then I should get back to this expression. I can always check myself by differentiation. Okay. So that's probably enough examples in that vein of thought. Let's talk about, what about that constant c? What if in my integration process, I'm given a integrand asked to find the indefinite integral, and I really don't like the fact that I have to add the constant c at the end? Given just a little bit more information about our original function, I can actually find that constant c. These types of problems are common in applications. We will call them initial value problems, or IVPs are commonly what their names are given. And especially in engineering contexts, these are seen a lot. Okay, so let's say we're given this. Let's say we're told that the derivative of a function g of prime of x is equal to 7x times x to the 6th minus 1/7. And then we're told a little bit more information. We're told that g of 1, not g prime, but g of 1 is equal to 2. This part here is enough for me to be able to find the arbitrary constant c. This we would call an initial value. An initial value, because this tells me what the value of g is, the function is, at the x value 1. So this tells me that when x is equal to 1, g of x, or the y value at that point x, is equal to 2. which is why these are called initial value problems. So given those two pieces of information, let's do this. Let's find g of x. I know its derivative, and I know the function value at one point. Okay, well, one thing I know is antidifferentiation undoes differentiation. So it's the backwards version of that. So let's see. I know that if I take the antiderivative or indefinite integral of g prime of x dx, then I should get g of x. Those rules of antidifferentiation undo the differentiation rules. So let's do that. This is equal to the antiderivative of the function 7x times x to the 6th minus 1/7 dx. So that is my goal. One problem here that I see is I have a product of two functions. I unfortunately have no product rule of integration. So my first step in solving this or finding an expression for it would be to distribute. I'm going to multiply this 7x by what is in the parentheses. So let's do that. Let's say, I'm going to write the function down. Antiderivative of 7x times x to the 6th minus 1/7 dx. I'm going to distribute. This is equal to antiderivative of 7x times x to the 6th is 7x to the 5th, or to the 7th, excuse me, to the 7th. There we go. Minus 1/7 times 7x would be just x dx, or x to the 1 if you prefer that. That one I know how to find the antiderivative of. I have rules that tell me how to do that. This is equal to, I'm going to apply my rules of antidifferentiation. Therefore, I am not going to write this integration symbol anymore. This is equal to the constant 7 times x raised to the 7 plus 1 power, which is 8, times 1 over 7 plus 1 is 8, minus x to the 1 plus 1 power is 2, times 1 over 1 plus 1 is 2. And that is all, plus that arbitrary constant c. I'm going to simplify this. This is equal to 7/8 x to the 8th minus 1/2 x squared plus c. And that's equal to g of x. That much I know just from my knowledge of antiderivatives. Okay, let's find this. Let's find C. Let's see, what do I know? I know that g of 1 is equal to 2. Well, I have a function for g of x. I have an expression for it. So I can use that maybe to find g of 1. G of 1 is 7/8 times 1 to the 8th power minus 1/2 times 1 squared plus c. And that all should be equal to 2. Well, now it looks like all I have is numbers, except for c. C is an unknown constant. I could use this to solve for c. Let's solve for c. Okay, on the left-hand side, 7/8 times 1 to the 8th power is 7/8 minus 1/2 plus c is equal to 2, which means C is equal to 2 minus 7/8 plus 1/2, which should give me, what is that? 2, negative 7/8 plus 1/2 is a negative 3/8. And then 2 minus 3/8 would be 13/8. So I know what my constant is. It's C, or it is 13/8. Obviously, it's C. So given that, I can write an expression for G. So that means G of X, I know exactly what it is without the addition of the unknown constant. It is 7/8 x to the 8th minus 1/2 x squared plus 13/8. So now I don't have the function G with an arbitrary constant on the end. I can tell you exactly what that constant is. Okay. Let us possibly stop this video and let's finish this section up in another video.